another video with math and physics fun with Gus. Today, we are talking about continuous charge distribution. So let's start off by a quick review of non-continuous charge distribution. So the total electric field and the force experienced by charge Q are given by the two equations. This is the total electric field, where you sum up a ton of point charges to find the electric field at some point distance this away in this direction, and then the force on that charge would be F vector is equal to Q times E vector. Okay, let's say you have a ton of these, and you have so many that it's continuously distributed over some surface, then the sum just turns into an integral. And, we love integrals. Integrals are fun. We love to do them. So, we have here the electric field vector, right? It's a vector, is equal to 1 over 4 pi epsilon naught, which is the same as this, but the sum turns into an integral of the direction, right, that the E field points in at some r script length away, and that's squared, times a small amount of the charge. So you can look really quick. Let's say you have just dq, simple, just one charge. You integrate over dq, you get Coulomb's law. Okay, great. Now there's charge densities we need to talk about. So charge per unit volume is just dq over dv, which is derivative of the volume. Sigma is usually dq over dA, which is area charge density, and lambda is dq dl, which is just length charge density. And these are very useful to find this dq. So you have some dq distributed over some volume, then you can get dq is equal to rho times dv, and then say you have some charged box, you can change dv into dx, dy, dz, and integrate over the cube. Okay, so now let's review this R script. I think it's really useful to understand what this is, this R vector, and it makes finding the electric field at some point really, really easy. So a quick review, we have R script vector points from the charge to the point we're trying to find the electric field at. So, and you can find this really easily by finding the vector from the origin to the point minus the vector from the origin to the charge. And that makes sense because say that this is placed at the origin, then R script, this is now the zero vector, and it just becomes R vector. So that makes sense, right? The closer the charge is to the point, the greater electric field it should experience. Okay, now let's talk about R hat. It just gives us the direction of the electric field, and that's just this vector over the length of that vector, and it's unit vector. So it has magnitude 1, doesn't change it at all, it just gives us its direction. Now we're going to do an example question, and in this example question, we're going to find the electric field at point P, which is on the z-axis, of a uniformly charged disk with charge density lambda centered about the z-axis at distance z away from the point. So this disk is perfectly centered. So what we're going to do first is we're going to find R script vector, and that's going to be equal to R vector, which is the distance from the origin to the point we want to find the electric field at, minus R prime, which is the distance from the origin to a small charge dq. So this vector goes from the origin to z, and that's equal to z hat, and this then goes from the origin for R prime, dq, some dq, and that goes from the origin to some x plus y, right? But you can also write this in cylindrical coordinates as s hat, where s is the length given by the square root of x squared plus y squared, and s hat gives s direction. And this is just writing it in cylindrical coordinates. So if you're not familiar with this, it's okay. It's not really that big of a deal. You'll get some experience in Calc 3. But again, just to reiterate, s is cylindrical coordinates. It's just the distance from the z-axis, and s hat gives s direction. So now what we're going to do is we're going to find the hat, which is going to be this vector divided by the length, c minus s, forgot my vector, c hat minus s hat, divided by the square root of the length of this, right, which is going to be z squared plus s squared. Remember now, s equals the square root of x squared plus y squared. So if we substitute s in for here, we get z squared plus s squared plus y squared, which is indeed the length. So this is this length. So we want to find now this script r squared, which is the length squared, and that's going to be equal to, well, this is script r, right? So this squared is this. It's going to be z squared plus s squared. Again, this can be written as z squared plus s squared, where s squared now is x squared plus y squared. Now we have this part of the integral, which is going to be this times 1 over this, script r hat over script r squared, which is going to be z hat minus s hat divided by z squared plus s squared 3 over 2. Now again, this is 1 over this, so you just take 1 over this and you times it through and you should get this. Okay, now let's look at dq. So we have this part of integral. Now let's look at dq. So we have that dq over dA, because it's a little amount of area, is equal to the charge density. So we can solve for dq by saying dq equal to sigma dA. Now dA is sigma dx dy, but we're dealing with cylindrical, so it becomes s ds d phi. D phi is this angle. ds is a small amount of length this way. Now we can integrate. We have everything we need to know to set up an integral. So we're going to have that e vector is equal to 1 over 4 pi epsilon naught times a double integral, because we have ds d phi, z hat minus s hat divided by z squared plus s squared 3 over 2 times now sigma s d phi. Now let's find out our bounds. So our bounds, well, d phi is this angle here, and it goes from this. Let me do this in it goes from here all the way around back, 2 pi. So phi is less than or equal to 2 pi, less than or equal to 0, and s goes from, well, it goes from the origin, and less than or equal to, well, the length of this disk, which I did not write, is capital R. So it goes from 0 to capital R. So now we have the bounds of our integral. So d phi is the latter, so it goes on the outside, and this goes from 0 to R. Now let's use some symmetries to simplify this integral. I see right away that this dq, the small amount of dq right here, creates an electric field at this point in this direction. If I take a similar point on the exact other side, so this creates a one in the exact opposite direction. Like if you rotate this and rotate this, you'll see that the only contribution, if you integrate over this entire disk to the electric field, will be in the z hat direction. So all the contribution from the s hat will cancel with itself, as you can see here. So there's like one pointing this way, but there's one pointing the other way. So we're not even going to have to do this integral. This is going to be 0 when we integrate it. So let's just get rid of it. Right? The less we have to integrate, the better. So we're now going to integrate 1 over 4 pi epsilon naught 0, 0 r 2 pi z sigma s z hat over z squared plus s squared 3 over 2 ds d phi. Now what we're going to do is we're going to look at constants in our integral. Well, z is a point, right? It's some point here. It's not changing, so that's a constant, so we can bring that out of integral. Sigma is a constant. S is changing, right? It starts at 0 and it goes over, so s is staying. Z hat is a constant, and z squared plus s squared is some really irritating function, so that also has to stay. So we can now write this as z sigma z hat for 4 pi epsilon naught times a double integral 2 pi r s ds d phi over z squared plus s squared 3 over 2. Now what I see is there's no dependency on s on phi, and vice versa. So that means if I integrate d phi, I just get a 2 pi. sigma z hat over 4 pi epsilon naught integral from 0 to 2 pi d phi times the integral from 0 to r s ds z squared plus s squared 3 over 2. Now, this is a really easy integral to do. This, on the other hand, right away I see if I use u sub down here, I'll get a 2s, and I can get the s's to cancel. So we're going to let u equal c squared plus s squared. Then du equals 2s ds, which means ds equals du over 2s. So which means when I substitute this in for the u, I'm going to get the same thing divided by 2s. So the s's will cancel. I'll get a 1/2 factor. So, okay, so we have this. Now let's look at our bounds. We have u now. U is less than or equal to. So u is less than or equal to z squared plus, well, the upper bounds of s are r. So it's going to be z squared plus r squared. And then the lower bounds are s equals 0. So then u at the lower bound is z squared plus 0, which is just z squared. So our bounds of integral are this now. So we're now going to get equals. I'm going to do this in white so we know we did the u sub. Again, we integrate 2 pi. d phi is just phi, and you substitute the bounds. It goes 2 pi minus 0. 2 pi divided by 4 pi, which is just 2 epsilon naught. Now we integrate from z squared to z squared plus r squared. And we get now 1 du over 2 times u to the 3 over 2. Again, we have this u comes this inside, which comes 3 over 2. The s's cancel, and you get a factor of 2 from here. Okay, so now what we can do is we can bring out the 2. We can write this as u to the minus 3 over 2, and then we have a really nice integral. And that now becomes, that's a horrible z, I can't write today. Z sigma z hat over 4 epsilon naught times now becomes u to the minus 1/2 divided by minus 1/2 z squared plus r squared. But this is going to be a negative, right? And then dividing by 2 is the same as timesing this function by 2. So we can take this negative and switch the bounds, right? Z sigma z hat over, well, this is the same thing as timesing this function by 2. So we can bring that out, and that becomes 2 epsilon naught. 1 over the square root u z squared plus r squared. Now we can substitute this in. Now we're going to factor this z through, and I'm going to bring the z hat and put it on the other side. So we're going to get that now. Our electric field is equal to sigma over 2 epsilon naught times 1 minus, oh, this should be a minus. Very sorry about that. Minus z over the square root of z squared plus r squared z hat. Okay, so this is indeed the electric field of a uniformly charged disk. I hope this video was useful. This is a more advanced application. So I'm Gus. We are Gus.